welcome to Intro 101. My name is Chris, and I am your neuroscience and psychology graduate student assistant. I'm here to assist you with the related science basics that you interact with on a daily basis. Now, the other day I came across a YouTube poll posted by a psychiatrist I follow. It was asking something to the effect of whether or not you should detox dopamine. I thought it was a very strange question, but of course his response was no, dopamine is not something you want to detox because it's necessary for so many bodily functions. Now, I'm not sure what prompted him to ask this question. I can only assume there's some kind of dopamine detox protocol or grift trending somewhere. So I thought it might be helpful to post an excerpt from my neuron physiology episode that describes the ways our neurons automatically clean up neurotransmitters, including dopamine, immediately after they're released. There's nothing left in the synaptic cleft to detox, unless you're taking compounds intended to prevent that process from happening. The excerpt also goes over the 4 main dopaminergic pathways and many of the ways our bodies and brains rely on dopamine to function in our daily lives. We even need it to make another incredibly important neurotransmitter. Now, I suspect the idea behind detoxing dopamine stems from dopamine's role in the reward pathway. I go into more detail in the excerpt, but the gist of the reward pathway is that when we are repeatedly exposed to a reward, we form an amazing feeling association to that reward. And once that association has been formed, it can continue to have a strong influence on our drive to seek more of that reward. And every time that reward is fulfilled, the drive to seek it and fulfill it gets stronger and stronger, until eventually it becomes a compulsion to seek and act on that reward. But to get control over this crave, seek, and act cycle and calm our reward pathway, we don't reduce our available dopamine, if that's what they mean by a dopamine detox. Dopamine is needed for so many things. What I can discern from the literature is that we want to interrupt the crave, seek, act cycle by cutting it off at the seeking part. If we don't seek the reward, we don't fulfill the reward. And if we don't fulfill the reward, we don't give the reward pathway, and any other pathways and neurochemicals involved in this dynamic, the chance to release and act on the postsynaptic neurons that would further strengthen the bond to that reward. The craving may remain strong for a while, but abstaining from seeking the reward will eventually quell the craving. Dr. Anna Lemke, in her book Dopamine Nation, calls it a dopamine reset. And it takes time. You're changing a habit. She says it takes at least 30 days to reset your relationship to this reward. Other researchers suggest adding another 30 days to form a new, healthier habit in relation to that reward. There are studies that support this reset in the context of social media addiction, but I'm not sure in what other life domains it's been studied. And important to note, this doesn't apply to recreational or pharmacological substances. Please get medical advice and a monitored plan before abstaining from long-term substance use. One last note before we get into the excerpt. I just want to gently caution anyone trying to alter their brain chemistry without medical supervision. None of your neurochemicals work independently of each other in a siloed manner. Neurotransmitters work in conjunction with each other and with other body chemistry like hormones. Intentionally increasing or decreasing the levels of any one neurotransmitter won't necessarily induce the action you're hoping for, or if it does, you may not be fully clear about the demands you're putting on your neural systems to compensate for that shift in homeostasis. Please discuss any concerns you have about your dopamine levels with a real-life licensed medical professional who is accountable to medical licensing and ethics boards in the real world and doesn't hide behind a disclaimer on social media. I'll post a link to the full episode I've pulled the following excerpt from if you'd like to learn more about neuron physiology, neurotransmission, types of neurotransmitters, and types of neurons, including mirror neurons. It was one of the first episodes I recorded for this channel, and probably the most words I'd said out loud in years, so apologies if it's a bit slow. My kids tell me it's best listened to at 1 1/4 times speed. Also, if you landed here because someone online is trying to sell you some kind of dopamine detox, you may also be interested in the mini-series I'm currently working on that examines the ways wellness influencers can take advantage of our decision-making mental shortcuts without our awareness to lock in our trust, loyalty, engagement, and eventually our dollars. I'll post a link to the first episode below. As always, thank you for watching and take care out there. Okay, lovelies, have a stretch, hydrate, because now we're going to look a little closer at neurotransmitters and what their roles are beyond propagating a signal to the next neuron. But first, we're going to look at what happens to them after they've done their business in the synaptic cleft. This part may seem like excessive detail, but this very tiny gap, the synaptic cleft between neurons, is a most beloved space. It's in this space where many therapeutic drugs and recreational drugs / drugs of abuse intentionally manipulate your brain chemistry, sometimes for beneficial outcomes, other times not so much. You may wish to know how and why this happens. So after the presynaptic button has released these neurotransmitters into the synaptic cleft and it is bound to the receptor channels in the postsynaptic membrane, in order for another neurotransmission to happen, the previous neurotransmission needs to be inactivated by removing the neurotransmitter from the synaptic cleft. This happens a few different ways. One is reuptake, another is degradation by enzymes, and lastly, it can just wander away from the synapse by way of diffusion. Reuptake is the fastest and most efficient way, and simply put, the neurotransmitter is taken back up into the presynaptic or terminal button to be recycled and restored in vesicles or demolished by enzymes. You may be wondering how it does this because the vesicle that housed this neurotransmitter fused with the presynaptic button membrane, so it's not going back into those vesicles. Well, much like ion channels embedded in the postsynaptic plasma membrane allow ions into and out of the cell, the presynaptic button has transporter molecules embedded in the plasma membrane that draws the neurotransmitter back into the intracellular space of the terminal button, and they are recycled and repackaged into vesicles. You may recognize the word reuptake because a certain type of antidepressant called selective serotonin reuptake inhibitors, or SSRIs, have received a lot of attention lately. Serotonin is a neurotransmitter, and we'll visit it in more detail in a minute, but SSRIs are a therapeutic drug that targets the serotonin reuptake transporter. So though normally reuptake is very fast, like immediately after releasing a neurotransmitter, an SSRI will slow the reuptake of serotonin by blocking the transporter, and this inhibits the transporter's ability to draw serotonin out of the synaptic cleft and back into the presynaptic button. The idea is that the longer serotonin can linger in the synaptic cleft, the more often it can stimulate the postsynaptic neuron. Though to be clear, we're still not super sure why SSRIs work. And indeed, in 60 to 70% of people with moderate to severe depression who try SSRIs, it will effectively help regulate their mood. Regardless, hopefully you're getting a clearer idea of what's happening at the synaptic cleft after the neurotransmitter has been released. The second way neurotransmitters are cleaned up from the synaptic cleft is enzymatic degradation, and that is when enzyme activity breaks down the neurotransmitter into its component parts that can either be recycled or diffused away from the synaptic cleft. The enzyme responsible for degradation is going to be particular to the neurotransmitter. An example of this process occurs when the neurotransmitter acetylcholine is released. It is cleaned up by both enzymatic degradation and transporter molecules. The enzyme acetylcholinesterase breaks down acetylcholine into choline and acetate molecules. The choline is drawn back into the presynaptic button by the transporter molecule and recycled to make new acetylcholine. I'm not 100% sure what happens to the acetate. I think it either diffuses away or may get gobbled up by other non-neuronal cells. And then the third mechanism of synaptic cleft cleanup is diffusion. Diffusion is when the neurotransmitter floats away from the cleft into the great extracellular space, like a bunch of George Clooney's in the film Gravity, except without the untethering drama. It appears this happens at just about every synaptic junction. There will be some diffusion of neurotransmitters even if the primary mechanism is reuptake or enzymatic degradation. So let's look at some of the different neurotransmitters and what they can do and how they're cleaned up from the synaptic cleft. Okay, So the next neurotransmitter is more than a neurotransmitter, but we're going to mostly talk about its neurotransmitterness, and that is dopamine. I don't know how to feel about dopamine. Is it friend? Is it foe? It's most definitely necessary. There's a number of dopaminergic pathways, each of which have very different functions involving multiple body systems. It's involved in craving and reward, motivation, learning and approach behavior, cognition, motor function, and prolactin regulation, which is involved in vastly different mechanisms from metabolism to sexual satisfaction to immune function. So all good things, right? But it's also connected to addictive behaviors, so the craving and pursuing of all those good things can become uncontrollable. So dopamine can be your best friend and also a bit of a sociopath. Or a micromanaging narcissistic boss who, if you enable, will lock you into cycles that siphon every ounce of autonomy and agency from your life. But if you just let it think it's the best of all the boss molecules running your body and occasionally affirm its business acumen, it won't bleed your soul dry, and it may even let you keep a plant on your desk. Okay, that's a bit abstract, but you'll get me if you listen to the many science educators and wellness influencers talk about it. I highly recommend the book Dopamine Nation by psychiatrist Dr. Anna Lemke. It's a really fascinating and intimate dive into the many facets of dopamine's effects on our behavior, but most notably addiction. What I'm qualified to tell you is that dopamine is both excitatory and inhibitory, and it is both a neurotransmitter and a neuromodulator. It may also be a hormone. It also makes norepinephrine. I mean, it's a bit of an overachiever and possibly a control freak, but we put up with it because, let's be honest, chocolate, thinking coordination, and orgasms are worth it. You're probably wondering how it can be both inhibitory and excitatory. It depends on the postsynaptic receptor channel. Dopamine has several subtypes of receptors, and some of them initiate an influx of sodium ions that make it excitatory, and some initiate an efflux of potassium ions that make it inhibitory. So what about these many dopaminergic pathways? There are 4 major pathways and many minor pathways. The majors are mesolimbic, mesocortical, nigrostriatal, and Tuberoinfundibular pathways. We could talk about each of them for days. I mean, everything in this episode we could talk about for days. It feels like I've been talking for days, so thank you for sticking with me. Hang in there a little bit longer. We're going to get into some of these major pathways. Okay, briefly. The mesolimbic pathway is the reward pathway, and it begins with a group of dopaminergic neurons in the ventral tegmental area, also known as the VTA, which is kind of near the upper front of the midbrain, which is at the top of the brainstem. Those neurons project to many areas of the limbic system, which is deep inside your brain above your brainstem. Most notably are projections that reach the nucleus accumbens, amygdala, and hippocampus. The mesolimbic pathway is the pathway that motivates us to seek pleasurable things, like food, sex, achieving a long, sought-after goal, anything that feels rewarding. It's also the pathway that, if not kept in check, will kick you in the teeth. Not totally on its own. The mesocortical pathway lends a hand as well, but it's mostly this pathway. It's lovingly called the reward pathway, but it's also brutally known as the circuitry that, with enough repetitive exposure to a reward, organic or artificial, can keep us compulsively craving and seeking more and more of that reward. For example, every like, share, and retweet you receive on your socials begets the craving and pursuing of more likes, shares, and retweets. And oh my goodness, when an internet celebrity, influencer, or whatever unexpectedly likes your comment on their account, or better, responds to your comment favorably, you feel amazing. And what happens is you form an amazing feeling association to that reward. And once that association has been formed, it can continue to have a strong influence on your drive to seek more of that reward for quite some time. This crave, seek, and act cycle can tether you to them without any assuredness of reciprocity. But it's that anticipation of reciprocity, that they may like or comment or respond again, that is what keeps you seeking more of that reward. And every time that reward is fulfilled, the drive gets stronger. The crave, seek, act cycle gets more and more repetitive, thus more and more addictive. And some of these influencers, and most definitely these platforms, bank on you being in repetitive, addictive crave and pursue cycles, because that keeps you on these platforms for longer durations. Now, I know all of you probably have a very manageable relationship with social media, but in the event that you ever find yourself feeling pressured to be in a constant contact with anyone on your socials, whether that's external or internal pressure, take a minute. If you're racing to comment on a post in hopes it will be seen and then keep checking to see how many likes your comment has, and if that influencer or any person of interest has acknowledged you, give it another minute. Give it many minutes. Give it all the minutes. Instead of posting or checking, put your device down and go outside if it's safe for you to do so. Take a tour around your block. Say hi to a neighbor, or call a friend and tell them how wonderful they are. Exercise, meditate, read or listen to a book like Dr. Lemke's Dopamine Nation. Interrupt the cycle. You can actually kind of reset this pathway, at least in this context. It doesn't mean you never check or post again, but you get to control when and why rather than letting when and why drive and control you. Now, I've never met Dr. Lemke. I have no relationship with her. I'm not trying to sell you books. You can probably find Dopamine Nation at your local library. What you may find helpful from her book is a dopamine reset protocol. This is not a dopamine fast. This is not a 24-hour reset. This takes time. She makes suggestions backed by rigorous research on how to break free of crave, seek, and act cycles, including over-engagement with social media. So that may be of some help to you. It was enormous help to me. Okay, so that wasn't really at all brief, but that was the mesolimbic dopaminergic reward pathway. Next is the mesocortical dopaminergic pathway. This pathway also begins at the VTA, again, that's the ventral tegmental area, but it projects to the prefrontal cortex, which is the top few millimeters of the surface of your brain at the very front. This area is where something called executive functions live, and that refers to cognitive functions and cognitive control. But dopamine's role in these processes has an excitatory effect on planning, reason, problem solving, attentional control, and short-term memory. Dysregulation of this pathway is believed to contribute to ADHD, addiction, and negative symptoms of schizophrenia. Okay, so that one was brief. Next up, the nigrostriatal dopaminergic pathway. This pathway begins with a group of dopamine neurons in the substantia nigra pars compacta, which is in the midbrain at the very top of your brainstem, and those project to basal ganglia, more particularly to the caudate nucleus and the putamen, which are part of the dorsal striatum. It's a lot of words you may not know right now, but we'll get to know them in a future episode. You'll recall a serotonin pathway also leads to basal ganglia, and that this group of brain structures is in the center of the brain and is responsible for movement, learning, emotional processing, and much more. Dopamine's effect on these structures is excitatory on GABAergic neurons, which then inhibit further striatal neural projections to influence voluntary movement. Why activate an inhibitory response to movement? Well, when this pathway is damaged, voluntary movement becomes uncontrollable or unstable. Symptoms of Parkinson's disease emerge when the nigrostriatal dopaminergic pathway is compromised from neurodegeneration in the substantia nigra. So in this pathway, dopamine is working in cahoots with GABA to help you maintain control over your voluntary movements, so you're not moving when you don't wish to. Okay, so the last dopaminergic pathway I'll talk about today is the Tuberoinfundibular pathway. This begins with dopamine neurons in the hypothalamus, which kind of sits at the top and in front of the brainstem, and these dopamine neurons project to the pituitary gland, which kind of drops underneath the hypothalamus. And I say drops because there really isn't a better way to describe what the pituitary gland looks like other than your brain's tiny scrotum. This gland connects the nervous system to the endocrine system, and dopamine's effect on this gland is to regulate secretion of hormones, in particular prolactin. Prolactin has a pretty vast CV. From maternal processes to sex hormone regulation to human social bonding to glucose regulation and appetite and metabolism, it has its fingers in a lot of pies. Dopamine's effect on this pathway is actually inhibitory. It's part of a negative feedback loop, hello homeostasis, and a negative feedback loop that stops the secretion of prolactin. Again, we have good reason to wish to inhibit the release of something. Elevated levels of prolactin can cause prolactinemia, which has been correlated, and by correlated it's not the same as causal, but correlated with obesity, insulin resistance, fatty liver disease, and infertility, to name a few reasons why it should be regulated. The regulation of prolactin release is important, and dopamine is the shutoff part of that regulation. So, those are some of the dopamine pathways. Dopamine is removed from the synaptic cleft by way of reuptake transporter, and related to health and wellness spheres, these transporters are a target for both prescription and recreational drugs. Much like the way SSRIs block serotonin reuptake transporters, the stimulant drug cocaine blocks dopamine transporters, preventing reuptake and allowing it to accumulate and linger in the synaptic cleft for longer periods of time. Cocaine is highly addictive. Going back to the reward pathway, when the rewards of euphoria, energy, and alertness is associated with the drug, the drive to seek more cocaine to get that reward elevates. But diabolically, the more exposure to cocaine someone has, the more the brain desensitizes to natural reward stimuli and simultaneously hypersensitizes the neural circuitry responsible for the stress response. So even the slightest bit of stress can drive cocaine users to seek out more cocaine. And it doesn't stop there. Repeated cocaine use increases one's tolerance to it. So you can see where this is going. More use at higher and higher doses. So you can get trapped in this cycle of rising cocaine use frequency and dose, which plummets coping capacity to the slightest stress, which leads to increased frequency and dose. And it gets worse. Repeated high doses of cocaine leads to developing sensitivity to its toxicity effects, which means the more someone uses repeatedly, the less is needed to launch them into anxiety, panic, convulsions, paranoia, potentially even psychosis. From there, we're looking at brain damage and loads of other organ damage, increased risk for stroke, brain bleed, cognitive deterioration, heart ruptures, movement disorders. It's really an unending list of all the ways cocaine can break down someone's body, yet keep them just alive enough to thoroughly experience their own deterioration. If I didn't articulate this well enough earlier, please don't mess with dopamine. Let it do what it's supposed to do, but do your best to not overindulge it. You've been a dream for staying the whole way to the end. Until next time, take care out there.